Hello, everyone, and welcome to this plenary session. In fact, it's a great pleasure and personal honor to introduce Thomas Berkemeier. Well, I don't know if it's well pronunciated, Berkemeier, from Max Planck Institute for Chemistry in Mainz. So Thomas leads the chemical kinetics and reaction mechanism group at the Max Planck Institute, where his work focuses on understanding the chemistry and physics of multiphase processes, both in the atmosphere and in human body. His team combines detailed kinetic modeling, laboratory experiments, data-centric approach, including machine learning, to shed light on the processes that influence air quality and human health. Beyond his scientific contribution, Thomas plays an active role in the research community, serving on the editorial board of Atmospheric Chemistry and Physics and on the steering committee of the Mainz Institute of Multiscale Modeling. On a personal note, I'm happy to say that I have recently the opportunity to work with Thomas through our newly European project Harmony. I'm truly looking forward to, well, in fact, with Jerome, and I'm truly looking forward to this collaboration and hope we'll enjoy developing this research. And well, today he will guide us through the topic of modeling the chemistry behind air pollution health effects, where we'll explore how pollutants like PM, ozone, and N2 contribute to the formation of reactive oxygen species. So please join in warmly welcoming to Dr. Thomas and enjoy the talk.
Yeah, thank you, Beatrice, so much for this nice introduction. So yeah, we have heard lots about the response of tissues to mechanical stresses today, right? So now this last presentation for today will more look about the chemical response. So what happens in our body, in our tissues, when we inhale air pollution? That's my research topic. So my background is I'm a chemist, but I'm an atmospheric chemist. So I mostly work in the field of air pollution. But don't despair. This presentation will not be too chemistry focused, and what it will have in common with the two previous presentations is that we're looking at mechanistic models. So we're trying to develop an understanding, what does air pollution do in our bodies that causes these known health effects of air pollutants? Okay, so my little agenda is, I think I will give a little bit of a larger background, because we here in this room, we are all not air pollution researchers, so I will talk about a little bit more what is air pollution and what are the effects of it. And then I will talk about the model that we're using. It's a kinetic model. And then the main part of the presentation will be this one. We'll be looking at the production of reactive oxygen species in the lungs and how we can understand this with models, both from air pollutants, but also from the endogenous sources that we already have in our body. And then at the end, if there's some time, I will look a little bit at the feedback mechanisms. What does the air pollution do once it's in the body? How does the body react and address it accordingly? Okay, so air pollution, I will focus today a little bit on particulate matter. So all the fine particulates that are in the air. Right? So what is particulate matter? We oftentimes call it PM. So, and if you look at this picture, right, so any picture of air pollution, typically what you can see are the particles. Right? So this is what obstructs our vision here. And in polluted air, we can have up to 1 million particles per cubic centimeter. And if you think how small 1 cubic centimeter is, right, you can really imagine how small these particles have to be in order to be in this cubic centimeters. And we can typically say that particles in the atmosphere have a size of smaller than 100 micrometers. So this is, the largest ones are maybe as big as the thickness of your hair, but they can be also much, much smaller than these 100 micrometers. Do you have an idea why there are not particles larger than 100 micrometers in the air? What might be a practical reason for that? Yeah? Exactly, they fall down, right? So we have particles in the air that are not very long-lived there. So like rain, if you think about it, right, or hail, or sand, dust that you put in the air. If it's too big, it falls down. So, but as soon as if it's really small, it can just really stay in the air for days, usually, typically until it rains or so. So even clean air, so even in this room, we will probably have several hundreds or thousands of particles per cubic centimeter. So they're everywhere. And so what are these particles? And this is it really depends on where you are in the world, of course, but a very typical composition is you have these salts in these particles, you have organic compounds, and also you have these kind of soot particles, black and elemental carbon particles, that make up this fraction of the entire cocktail that you have in the air. And maybe something you've heard before is PM2.5. So when I say that, this is the mass of all particles smaller than 2.5 micrometer in the air. And the reason we're limiting ourselves to 2.5 micrometers here and not 100 is that this is what really goes deep into the lung and causes your health effects. Okay, so maybe just very briefly, how does this particulate matter form? So either we can emit it primarily, right? You see these furnaces here, or your exhaust from cars and so on. So here you put particles directly into the air. There's also natural processes that make particles. For example, this wave breaking, right? This brings lots of salt into the air. And also something that's on the chemistry side very interesting is the secondary formation. There's actually a lot of particles. Roughly half of the mass of these particles in the air come from the secondary organic aerosol formation. So what happens is you have emission sources like trees, but also cars, who emit volatile organics, right? These compounds here. And then you have compounds like ozone that oxidize these organics. They get a low vapor pressure and they start condensing onto particles. And because this is a bit complicated, I have brought here this little video of a kitchen table experiment where you have these orange peels sitting down here. They emit these volatile compounds, and someone injects ozone here. And then this is exactly what happens here, right? You have this kind of chemical reactor where the volatile compounds from these orange peels, this is limonene, is oxidized, and you can see this white fog that are particles that are being formed here. All right, so lots of what you have in these urban areas is actually formed through this pathway. Okay, so this is what these particles are, how they are formed. The other thing we have to know is they are everywhere, and they are also transported over long ranges. So this is a large-scale chemical transport model, or sometimes you could say it's an Earth system model. This is not today's topic, so this is not the type of modeling I do, but I think it's interesting to see the broader impact, what people do. So for example, here you have different sources of these particles. We talked about the sea spray, but of course also there's traffic and or dust, and you can really see this like traffic or industry focus or dominated particles that here you see over Central Europe, right, how far it's actually being transported. So it's not just a local problem, it's not just a street that you have outside here, but it's more like the entire regional or continental area that can cause these particulate concentrations. So this is important to have in mind, and we'll get back to this a little bit further. Okay, so today I want to talk about the health effects of these air pollutants. So a very general overview would be there's 3 principal air pollutants that you have to have in mind when you regulate air pollution. So it's this particulate matter smaller than 2.5 micrometer we talked about, PM2.5. There's ozone as an oxidant, and there's what we call NOx. So these are like nitric oxide and nitrogen dioxide. So these are what typically causes most of the health effects. Today, I will focus on this particulate matter because epidemiology says that this has the biggest impact on our health, right? So, and maybe what you've seen, right? You have seen this picture here. There's air pollution in these big urban centers, and maybe you have also seen stuff in the newspaper that says, wow, worldwide, 9 million people die from air pollution every year, right? Or here, the World Health Organization calls air pollution the silent killer, and here they speak about 7 million deaths every year in the world, right? So this sounds big, and I guess you can all imagine that in these urban centers there will be lots of health problems due to air pollution, but I think the connection between these two is not so straightforward, right? So how do I get from here to people actually dying and not just being a little sick or so? Right? And so now we dive into the realm of epidemiology. This is also not my field of study, but I think it's really important to kind of know where these numbers come from. And this is now a busy slide. I will walk you slowly through it. On the right side, you see kind of the combined evidence that we had in the year 2010 that was combined here, how air pollution affects or air pollution in terms of particles affects mortality, right? So what all these studies looked at is what the percent increase in mortality upon increase of PM2.5 where you live of 10 micrograms per cubic meter. So let's put this 10 micrograms per cubic meter aside for a little bit, but this is a percent increase in mortality, right? And you see the numbers here roughly are somewhat on the order of like 10, 20, 30%. This is what these studies find. And so here we have the increase of all-cause risk. So I'm going to do a very basic back-on-the-envelope calculation now, right? So I'm just pointing a line here that said, okay, I think if you take all these studies together, maybe there's a 10% increase in mortality when you increase pollution by 10 micrograms per cubic meter. Okay, so typical urban areas, I can tell you this now, you maybe find these PM2.5 concentration of 25 micrograms per cubic meter. And if you really go into the rural areas, maybe you always have a background of maybe 5 micrograms per cubic meter, right? So there's an increase of 20 micrograms, and we learn from here, right? Every 10 micrograms gives you a 10% increase in mortality. So your all-cause risk of dying, right? Your risk of dying every single day from disease is increased by 20% when you go from like rural areas to urban areas, right? This is if you really want to brush this down to some details, this is kind of what you have to expect. And I would like to do another little kind of like calculation exercise just to give you a feeling what this means. And so I like to compare it to the kind of best studied case of like mortality in epidemiology, which is smoking, right? Smoking is pretty easy because either you're a smoker or not, typically. There's not very many people who just smoke an occasional cigarette a month. And there's this great study where they looked at British medical doctors, and they're all born, so this is a very old study. They were born in between 1900 and 1930, and they have a huge sample size here, almost 35,000 people, so this is a great study. And so what this plot now shows is how many people are still alive at a certain age, right? So they started with all these people. They followed at the age of 30-something, right? And here everyone was still alive. And then they looked over the time how many people at a certain age are still alive. And what they saw is that the non-smokers here at the top, right, they died at a slower rate than the smokers. For example, here at age a little bit above 50, 97% of the non-smokers were still alive, whereas only 94% of the smokers. And what you can kind of see is this is almost a twofold rate, right? So here at the age of 70, only 20% of non-smokers had died, but about 40% of the smokers, right? It's always double. And what we call this a hazard ratio of 2, or an all-cause risk increase of 100%, right? You're twice as likely to die on a given day when you're a smoker compared to a non-smoker. So let's now compare this to air pollution, the number I gave you on the last slide. So we said maybe it's an all-cause risk increase of 20% or a hazard ratio of 1.2%. So just to kind of give you an idea what would be if you could switch off air pollution in your city for your entire life, it somewhat means that, especially when you look here in the end, right? So here the numbers actually, they get quite staggering. The people who reach the age of 90, right? There's quite some difference here between the 24% that would be alive in an ideal case versus in the case with air pollution. So here you can kind of see that we all lose roughly a lifespan of 2 years due to air pollution when we live in this urban center. And this is where, if you really sum it up over the entire world, then you get to these 9 million deaths per year caused by air pollution, right? So this is kind of the epidemiological basis. And how this is now calculated for a given place, it works like the following, right? So instead of the hazard ratio where I just said, oh, hazard ratio is 1.2 everywhere in the world, right? So people do this much more elaborate and complicated, right? So here, for example, you have for a specific disease, for a specific age group, you have these hazard ratios, and they typically do it as a function of this PM2.5 concentration, right? I just said, okay, we go from 5 micrograms to 25, but here this is a bit more elaborate, and they have these hazard ratio curves. Then they look at, okay, where do you live? What's the air pollution exposure in the place you live? We already saw these Earth system models, right? And then you get to these estimates of excess mortality. Okay, so this is the methodology that produces these numbers where, oh, maybe in Asia every year 4 million people die from air pollution. So when I look at this as a chemist now, so I have now a few questions, right? So one is, when I look at this curve is, so they start at some point, but they also don't, so these are two different studies. They don't really agree on where to start. So is there actually a safe exposure level? Can I reduce air pollution so much that there's no effect on my health? That's an open research question. Then I look at these curves at the end, and one kind of levels off, and the other one just keeps increasing. So what happens here? We don't know, right? This is just from epidemiology. And also, I look at this and see they only put particle mass here, right? So they don't differentiate where does the particle come from, right? Is it from the sea spray, right? Is it just ocean salt being raised into the air? Or is it dust? Or is it traffic pollution, right? So they don't differentiate that. And I, as a chemist, so I have a problem with this. So this is my motivation. What I want to solve with my research are these questions, right? And before I get to the models, there's one very popular method in atmospheric science, and it's called oxidative potential. And it's quite interesting because it already goes into the direction that my work goes into. So what people do is they sample these particles, so they go outside, collect these particles on a filter, and then they put this filter into an antioxidant solution. So and the antioxidants they are typically used are ascorbic acid, vitamin C, or DTT, so this is a thiol. And they mix this together, and they look at how much of these are depleted after you mix it. And then you can actually determine which components of these particles actually cause these antioxidants to deplete, right? And what people learn here is the transition metals, copper, iron, but it's also carbon, so organic carbon and elemental carbon. So these are the main culprits of these of depleting these antioxidants, which is the same process that would happen if you would inhale them, right? So this is a great hint that somehow redox chemistry must be playing a role in the way where how air pollution causes health effects. So my goal, the goal of my work, is to connect what we know from atmospheric chemistry, so atmospheric pollutant concentrations and the composition of these particles, and this epidemiological evidence that I have been going over the last 10 minutes. And because I think there's a gap. There's no mechanism that connects these two, right? So these are two different research areas. And our approach is to bring those together. So first through kinetic laboratory experiments, field measurements, and in vivo studies. And we use these multi-phase chemical kinetics models to bring all this together. And just as Beatrice has mentioned, we have these nice EU grants that we're involved here. Okay, so we want to find a quantitative chemical rationale for the health effects of air pollutants. And so to repeat the hypothesis again that goes into these models, right? So we say we have air pollutants that we inhale that cause the generation of free radicals. It's not quite clear how this works, so this is a question we have. Once we have these free radicals, how do they cause oxidative stress? This is another research question. And then the mechanism that we think is going on is that you have a feedback loop of oxidative stress and inflammation that just goes around and around. And at the end of this, there's disease, such as these inflammatory diseases, COPD, asthma. They may be heart disease, and they may also be cancer. And the place of the free radical generation, we think, is the epithelial lining fluid of the lung. So and this brings me to the kinetic modeling approach that we're using. So what is this epithelial lining fluid? So the model we're using we call KM-SOP-ELF, the kinetic multi-layer model of surface and bulk chemistry in the epithelial lining fluid. And what this model does, it looks at, okay, so what pollutants do you inhale? So PM2.5, ozone, NO2. These pollutants now, they dissolve or deposit in the lung. And what lines the lung is this epithelial lining fluid, right? So you have a thin mucosal layer that sits on all the epithelial cells in your lung. And the pollutants go in there. and then they undergo chemistry. So they undergo redox chemistry and produce these reactive oxygen species. So this is hydrogen peroxide, superoxide, ozone, OH radical, and so on. And now what we do is we try to estimate the health effects of air pollution by measuring how many of these reactive oxygen species are formed in a lung. And we'll get back to this, this plot on the right side, but it typically looks like this, right? So we have on the x-axis, again, this PM2.5 mass concentrations. We look at the production of these reactive oxygen species. So here's hydrogen peroxide, superoxide, OH radical. And then you'll see later there's some dots that are measurements, and there are some lines that are models. But this is how our models work. So these kinetic multi-layer models, they are combined chemistry and physics models, right? So we really look at the chemical mechanism and all the physical processes that happen in these multi-phase systems, right? So if you think of a multi-phase system, so in the middle you have something that's like a condensed phase, a liquid or so, and on the outside you have a gas phase. In the model picture, maybe it looks like this, right? Gas phase on top, condensed phase at the bottom. And what we now do is we solve all the chemistry and physics, right? So we have gas phase chemistry here, we have condensed phase chemistry here at the bottom, and we also look at how all these molecules, how they can like diffuse towards the surface, go sit on a surface, and then diffuse inside. So we solve a set of ordinary differential equations that tells us how all these chemical species evolve over time and space, right? And yes. And the model that we use, we call it KMMO. So it's a model generator that translates the chemical mechanism and the system geometry in a set of differential equations. Okay, so now I would like to talk more about what is in this computational model KM sub alpha. What does it actually do? What are the chemical reactions inside the model, right? So we'll again look at our three pollutants, ozone, PM2.5, and NO2. And this is now a very, very simplified view of what happens in the model. So there's many, many other chemical reactions, but I will really focus now on these few and go through them kind of step by step. So this is what we do to estimate the health effects of air pollution. Okay, section 3. So first of all, we look at what the air pollutants do. So I will go through this now step by step. And I will want to give 5 general takeaways that kind of summarize what the model does in general, and then we'll look at specific scenarios. Okay, so what do we do in general? First of all, we have to look at the redox cascade. So what do I mean by that? We start with oxygen typically in a cascade, which is reduced to this O2 minus radical, this we call superoxide. H2O2 is hydrogen peroxide. And then at the end of this cascade, we have the OH radical. And these reactive oxygen species, they're constantly formed, interconverted, and scavenged. And this entire process, this chain, is catalyzed by the particles, right? As you can see here, you have copper and iron, which are contained in these particles, and they turn over these reactive oxygen species into each other. Very important. Second, let's look at the gas NO2. So the role of NO2 in the model is mainly to scavenge antioxidants, right? So this we had before. AO always stands for antioxidants, and it also produces a little bit of the superoxide. Same with ozone. It reacts with antioxidants, but it also can react with lipids that you have in your epithelial lining fluid, and that can form peroxide. So this can make this H2O2 here. Good. So what happens with H2O2? This is a very central reactive oxygen species because it's very stable. So if you look at, if you would probe the lining fluid in your lung at one given point in time, most of the reactive oxygen species will be H2O2 because it's the one that reacts the slowest. So we have most of this here. So it's really interesting chemically to see what happens. So, and because we also have enzymes in our body like catalase that scavenge H2O2, right? So this makes it more or less unreactive. But there's a competition. There's a competition between the enzymes that you have here that just delete or deactivate the H2O2 and the copper and iron, these transition metals and other compounds that activate H2O2 into the OH radical. The OH radical is super reactive. Whenever it's formed, it just reacts with anything, with all biomolecules. And this is my last takeaway, is that these hydroxyl or OH radicals, they cannot be scavenged, right? The body has no real way of dealing with them. Yes, you have antioxidants, and they do react with antioxidants, but you have so much more other molecules around, like lipids, proteins, and so on, your cell membranes, that once these OH radicals form, we think they cause oxidative stress, right? So this is one of the main culprits here for oxidative stress in the lung. Okay, so these are my 5 general takeaways generally about what the model does. There's many other chemical reactions, but these are the main strokes. Okay, let's now take a deeper look at the model output. So as I said, we often model Ross concentration. So these are now all model results. Again, we look at this as a function of this PM2.5, so the mass of particles in the air at a given place in the world, and look at what is the concentration of Ross in the lung or in our epithelial lining fluid. And now every marker is a model result for a specific PM2.5 composition that someone went out and measured, right? They went here to Barcelona, for example, measured the particles in the air, and then wrote in their study what is in the particles they found. And what we looked at here as particle composition, we looked at the secondary organic aerosols that I spoke about in the beginning, then transition metals such as iron and copper, and then quinones, which are these polycyclic compounds that you often find in soot particles and so on. So these were the 4 main redox active ingredients that we looked at. And you see, if you compare the composition of all these measurement stations that we looked at here, right, they somewhat cluster around a central value. And this median value we also took in order to obtain the solid line, right? So if you assume all the particles all over the world are the same, then you would always just look at this line. But the main observation that I want you to take away from this figure here on the left is that the particle composition matters, right? And it causes this variability in the concentration of Ross that the model predicts for the lung. For example, let's take just 2 points, right? So you see 1 point up here, right? So we are somewhat at 100 micrograms per cubic meter of pollution. So it's already a very polluted city. So this was a measurement in Guangzhou in China. And then there's another measurement or another particle composition we use in the model. This is from Karachi in Pakistan. And even though the PM2.5 mass concentration is almost identical, we predict very different Ross concentrations in the lung, right? So this is finally what we wanted, where we not only look at the mass of these particles in the air, but also what exactly is in the particles, and that gives a stark difference in the response that the body might have. Great. So let's take an even deeper look. You already saw this figure, right? So let's look a little bit deeper into what are the reactive oxygen species that are being produced. So I mainly look at superoxide, H2O2, and OH radical. This is, again, our redox cascade. And I already told you that we are mainly interested in this OH radical, because that's the one that really causes the oxidative stress. Also note that there's a log axis now here. And also, the H2O2 has a big importance, right, because it's so stable. And if you now look at the difference between the blue curve and the orange curve, you see is they are narrowing down, right? So they're getting closer as you go to higher pollutant concentrations. And another way of displaying that and what the model tells us is that the conversion from H2O2 to the OH radical becomes more effective as you go to higher pollutant concentration. So this is the fraction of H2O2 molecules that are being produced, converted into OH as a function of this pollutant severity or pollutant concentration. And you can see it really increases as you go higher. And this is because of the Fenton reaction, right? Fenton reaction means iron reacts with H2O to the OH. As you have more of these inhaling more of these transition metals, this reaction becomes more efficient, and there's somewhat of a tipping point behavior, right? So at this point here, your enzymes, they're still doing a good job at scavenging all the H2O2. As you go to high pollutant concentrations, your enzymes, they don't stand a chance anymore, right? There, it's just the transition metals that are turning over the H2O2 in your lung and producing these noxious OH radicals. So you have an overload of your body defense mechanisms. By the way, if you look at Guangzhou, China now I made it a green point, because now we see, oh, actually, the produced OH concentration is really small here, right? So the only reason we had lots of H2O2 in the first place is because we're not converting it to OH. And this is maybe a little side lesson here, is you have to kind of look at the entire portfolio of reactive oxygen species in order to like make a gauge or decision of like what's actually happening in the human body. Okay, so I talked a lot about like H2O2 and OH radical, but in the end we have to compare our model with observations, or have to find some kind of underpinning of saying, so what's actually now bad, right? So do I look at H2O2, do I look at OH radical? And one thing that people often do is to look at biomarkers. And a biomarker of oxidative stress in the lung is 3-nitrotyrosine. So this is what people often look at and use, and they find it elevated when there's oxidative stress. So we added a comprehensive chemical mechanism of tyrosine modification, so the formation of nitrotyrosine, to our model, in order to let our model say when you would form this biomarker for oxidative stress. I'm not going to go through this mechanism, the schematic mechanism now. Just know that there's two ways of forming these reactive intermediates. One goes only through this OH radical, and one also involves ozone and these nitrogen dioxide and so on. And but this pathway, there's no repair pathway possible. Here you can have a repair pathway with antioxidants. So this is yet another reason why we think that this OH radical is so important for air pollution health effects. So what the model now says is the following, right? So as you now increase air pollution severity, now I threw away my PM2.5 axis. Now I simplify this a bit more into what is when you're in a remote location, rural location, when you're indoors, when you're in an urban center or in a very polluted urban center like you would find in India or China, right? So and in here you can really see that the model predicts that this concentration of nitrotyrosine in the lungs increases quite drastically when you go to these urban pollution scenarios. And one interesting side effect that also our model produces is there's these medical studies that say, well, there's lots of in a kid when it grows up in a household that has a gas stove in the kitchen is way more likely to have inflammatory disorders like asthma when they grow up. And what actually our model also shows is that if you take the particle concentration of these indoor air, but switch on NO2 that is typical when you're operating a gas stove, you actually really increase this marker for oxidative stress in the lung to a level that's very comparable to urban city air. Right? So this is quite a remarkable finding. Just comes out of the model, and it somehow matches these anecdotal evidence that we have that when children grow up in households that have a gas stove, right, something is happening. There's some oxidative stress happening in the lungs, and the model now kind of with this mechanism finds somewhat of a mechanistic reason for that. Okay. So we looked at the production of ROS from air pollutants. Now let's compare it with endogenous sources. And this has been some more newer model development that we've been publishing in the last years. So this, again, is the model that I've been talking about with you, maybe a little bit different schematic now. But again, what we said is that H2O2 is a very central ROS molecule. It sits here, because this is the branching pathway. It either goes into the enzymes, or it goes into this noxic OH radical. But of course, our lung is not just the epithelial lining fluid. You have cells, and you have also blood vessels underneath. And these cells, they also have lots of enzymes, right? And the H2O2 can travel really from the gas phase outside into the cells. It may be produced from the cells. It may also be scavenged in the cells. And there's also a reservoir of H2O2 in the blood. So now we call this model KMSF 2.0. It's the new evolution of this model where we try to take this into account. So what happens here? First of all, I want to give you a feeling of H2O2 concentrations in all the different compartments of the body. Let's start at the bottom. In cells, the numbers don't really matter, but maybe the order does, right? 1 to 10 nanomolar of H2O2 is a background, like a physiological background in your cells. if you now probe the exhaled breath condensate, so what you exhale, and then you condense out the liquid, and you measure how much H2O2 is in there, it's 10 to 100 times higher. So you measure around 100 nanomolar of H2O2 in your exhaled breath condensate, so it's somewhat enriched already in this condensate. Then somehow your blood has an even higher concentration of H2O2, so 5 micromolar in the blood. And then in the atmosphere, so if you have just a water droplet in the air, there is so much H2O2 also in the ambient gas phase that dissolves into this water droplet that you have concentration of 100 micromolar, right? So all of a sudden, we're talking about a difference of 4 or 5 orders of magnitudes here between what is in the atmosphere just as a gas and what is in your cells. And somehow the model now has to cope with this. And what we found when we were putting together the study is that there's one parameter that's really important. And this is the permeability of your cellular membranes to H2O2. That makes sense, right? Because you're in your cells, you have lots of enzymes that can consume H2O2, and you have lots of H2O2 coming from outside, from the gas phase here at the top, right? And in order the barrier between the two is really important. So we had a rough idea where this permeability coefficient should be, so it's somewhere here. But what we also saw is that it has a huge influence on the model. So as you go to the left, right? So here it's the H2O2 concentration in the epithelial lining fluid. It goes to this minimum, right? On the very left, so where the difference between your epithelial lining fluid and your cells is very large, right? Whereas on the right, if your membranes are very permeable, it's just the same. So on the left, the H2O2 concentration in your lung is controlled by the ambient air, whereas on the right here, the H2O2 concentration in your lung is just determined by your cells. And we think we're somewhere in between, but it's actually pretty close. Also, what you see is that, so this orange line now is what the model predicts for the H2O2 concentration in the cells. And here we are at our best guess value. We're actually within this orange band that we know from the literature, right? So it seems like our model is doing a good job at predicting these concentrations. Good. So the model result here is now constrained by these physiological parameters. And now I kind of want to, we did lots of studies here. I just kind of want to summarize it with a slide. So what we now find with the updated model, let's look at the H2O2 sources. Where does H2O2 come from in the model? And before I said, well, it all comes from the particles, right? We looked at H2O2 coming from the particles. When I ask this model, where does the H2O2 come from? The particles here, PM2.5 in gray, it's just 1%, 1.2% for these different conditions that we looked at. So even the urban conditions, right? Polluted urban conditions, lots of particles, just 1.2% of H2O2 comes from these particles. It actually comes from endogenous sources, right? Here in the red, this is what the body anyway produces in H2O2, and or in blue here inhaled from the ambient air. So particles don't even matter. Isn't it strange, right? I told you in the beginning, 9 million people die every year from inhaling these particles around the world, and now I'm telling you they actually don't make any ROS in the lung. Well, if you move on and not look at H2O2, which you anyway have in the lung, but look at, again, the production of this super reactive OH radical, then the picture becomes more clear again, right? Now we have as we increase the particle concentration, we have first of all, there's almost nothing here on the left side when there's no pollution, and you have this, so this is a logarithmic axis here, linear axis here, OH production against PM2.5 concentration, and right, so here you again have this super linear response of the OH radical production that directly follows the particle concentration, right? So we established OH really triggers oxidative stress. It really depends on the amount of inhaled particles. So PM2.5 is not the fuel, right? It doesn't provide the reactive oxygen species, but it turns them into the more reactive ones, right? And this is currently our hypothesis that the model delivers that triggers these air pollution health effects. Okay, last little section for today. Now it's getting a bit more complex, right? The model is getting more and more complex, and now we also want to add some feedback. So here, again, you see our model KM sub ELF. We talked about this lots now. I want to add one more element to it. And this is, so we talked about these OH radicals that we produce them, and we think they trigger oxidative stress. This is not part of our model, but this oxidative stress will trigger inflammation. What happens when you have inflammation in the body? One thing that happens, your body is producing nitric oxide, NO, itself, right? So this is somewhat of a, you could say, a hormone. It acts as a vasodilator. It triggers the activation of macrophages, right? So this is really part of your immune response, of your inflammation response. And in this study, now we looked at what does it do chemically and how does it interact with the pollutants that you have, that you inhale into your lungs. Well, NO reacts with superoxide. We already said, okay, we're producing some superoxide from our body and also from these particles. And here you're making peroxynitride. Peroxynitride can also make OH. So this is not oxidative stress, but maybe nitrosative stress, right? So this is another element that comes with it. Okay, so we wanted to investigate this. First of all, we had to see how much of this NO do you actually have. And PhD student in my group, he looked into many different studies and compiled the concentration of exhaled NO. This is something that in the medical sciences has often been measured. How much NO do you exhale? It's a marker for the inflammatory state of your body. And so the numbers that we found is that they were usually, so we looked at 21 studies or cohorts, and that on average in control, so in healthy people, you exhale 9 ppb of nitric oxide, and patients with inflammatory disorders such as asthma or COPD, so the variability was huge. But on average, they exhaled 28 ppb. And what we then said, okay, the absolute change differences are so big, but actually the relative differences, they were more or less consistent, and this depends on how you measure and so on. So we said 2 to 4 times increase in this nitric oxide concentration. That seems to be what happens when you have this inflammatory disorder. Okay, 2 to 4 times more. So now let's dive a little bit more into the chemistry, what actually happens. So we have one reaction. So what happens with the superoxide? That's what I'm asking now. And so we have the enzymes here in green, right? So they make from superoxide, they make H2O2 and O2. This is a dismutase, superoxide dismutase reaction. Then we have the PM2.5 constituents. They also convert superoxide into H2O2, this time not deactivating half of it, but just converting it. And now the new reaction, right? NO plus superoxide making peroxynitride. And you can now see on the x-axis here is at how much exhaled nitric oxide, which of these reactions dominate. This is what our model can do, right? We can feed it in this exhaled nitric oxide concentration, and then we kind of assume a typical urban air pollution scenario, but this is not so important right now. And you can kind of see as you increase this exhaled nitric oxide, up to 50% of the superoxide can be converted into peroxynitride. What does peroxynitride do in the body? So we roughly approximated the fate of this peroxynitride. A lot of it is scavenged by antioxidants again, or reduced into nitrate. However, roughly 10% is converted into the OH radical. Right? So, and running with this OH radical, we can now ask what are the sources of OH as a function of this exhaled nitric oxide. And we find that, well, if you don't exhale much nitric oxide, the OH mostly comes from the PM2.5, from the particle constituents. So this is your transition metals, iron, copper, and so on. But if you, as you increase your inflammatory state, with increasing ENO, more and more comes from this peroxynitride. And again, we can reach almost 50% here. These are admittedly very high numbers, but yeah, it's what I want to say with this is it is significant. It makes a difference. So almost the last complex figure for today. This one's really complex, so let's take some time. Again, what we have here on the x-axis, PM2.5 concentration, so how bad is air pollution? On the y-axis, again, we have our exhaled nitric oxide. So this is somewhat the inflammatory state of a human being, you could say. So if you go from not having asthma to going asthma, you're going up in this figure. And as you go from like a nice rural city or so, or like a town, to an urban center, maybe such as Beijing or Barcelona, you go from left to right. And maybe just to give you, so the model, of course, can simulate all of this, but the most relevant conditions that we found, so for the inflammatory response and also for typical PM2.5 values, you could say you're mostly in this rectangle here. If you're in polluted cities in China, you could maybe be here, but usually you are within this rectangle. So now what does the asthma or the COPD, the inflammatory condition, do? So we're moving up. So one thing I have to tell you, what's the color? So the color is how much of your superoxide is converted into the OH radical. So the more red, the more of the really noxious radicals are being produced in your lung. Okay, so what do we see as we go up? It goes from blue to green to orange. So the fraction of OH radicals being produced goes up when you have these inflammatory disorders, right? A higher fraction of OH per superoxide molecule is being produced. And then as you go to really high pollutant concentrations, it actually doesn't matter, right? Here, so the isolines of this plot are vertical, which means it doesn't matter if you have asthma or not, you anyway make lots of this OH radical. So here there's a negligible effect, but the important message is that here you are sensitive, right? Especially here on the left side, right? Here the lines are really horizontal, and here they start to become a little bit vertical. Now, if I want to summarize this previous figure into one that's a little bit easier to digest, again, PM2.5 concentration on the x-axis, and what I now put here is the additional OH radicals that your body produces because of this inflammatory disorder. So I told you in the very beginning, 2 to 4 times the amount of nitric oxide is what you produce when you have asthma or COPD. So these are these lines here, right? So here this model assumes 2 times more, this model assumes 3 times more, and so on and so on. So if we now compare this with like typical air pollution guidelines, right? WHO says do not go above 5 micrograms. In the EU, actually the guideline is 25 micrograms. All right, so if we, within this space, and then look at this 2 to 5 times increase of ENO, we can say that the production of OH radicals, so this is what triggers oxidative stress in the lung, is increased in these individuals with inflammatory disorders between 5 and 35%. All right, so we have an increased susceptibility of people with inflammatory disorders to air pollution. Right, and this is very, I think this is when you're like a medical student, this is very intuitive, that if there's air pollution outside and you anyway have a lung condition, right, that you are way more susceptible to these health effects. And here with this study, we see kind of almost a chemical mechanism of how this could be. It's only 5 to 35%, but of course this is only one chemical reaction essentially that we looked at. Right, so this is just one reason. Okay, so to summarize. I hope I was able to showcase our model, KM sub 2.0, as a tool to provide a molecular process level understanding of health effects, where we try to bridge the gap between what we measure outside and what people find in epidemiology. We can look at the differential toxicity of air pollutants. So which ones are more toxic than others? How does it really depend on what the composition of your particles is outside? We look into molecular mechanisms of the oxidative damage by looking at this nitrotyrosine production and so on. And we find a rationale for the increased susceptibility to air pollution in these diseased individuals. Biomarkers we explored is this 3-nitrotyrosine that our model can predict. And I also hope I could show you the importance of the production of these OH radicals in the lung. The sources of OH radicals are peroxynitrite, which comes from these inflammatory feedback loops, but also decomposition of peroxides with this Fenton chemistry that comes from the particles that you inhale, right? And so this might not interest you much, but in my community, it's a huge thing to look at the total ROS production of pollutants. And I think I showed you in the beginning these oxidative potential assays that essentially look at how much total ROS is being produced, how much antioxidants are being consumed, However, our models kind of show that this might be less important because your lung is anyway in a redox homeostasis, and what really matters is the production of these super short-lived radicals, and they also then really trigger the production of these compounds that are known biomarkers for oxidative stress. Okay, so and with this, I would like to thank you for your attention, thank my team and collaboration partners, and I'm happy to take questions.
Time for questions or escaping to the countryside. I don't know if any of you want to say something. Laura. Perfect.
Thank you, Bea. Thank you very much for this very nice talk. And it's actually not at all my research field, but I'm really interested in this. And you made it really clear. So
thank you.
It's a really great talk. My question would be from slide 18. Maybe this is the wrong interpretation of mine. Yeah, exactly here. Like this line that you have, let's say...
here?
Exactly this one.
Yeah.
This somehow maybe suggests that you have a saturation at the higher levels of this PM 2.5. Like, is there, I don't know, like if I look at this, it looks like it doesn't kind of go up anymore. It's kind of stable, right?
Yeah.
So does it mean that the lung has a highest level of being able to kind of deal with those particles, or is it just a guess, or like, yeah?
Yeah, it's super interesting. So this is a study that's a little bit older. When we saw this in the beginning, we were super excited, right? Because also what epidemiology finds, right? You also see these curves that somehow they start at some point and then they shoot up, but then it levels off. Also, we know from smoking. So if you actually would look at the amount of inhaled PM 2.5, so this is ambient air pollution when you go outside. When you're a smoker, so you don't fit on this line, right? You're somewhere here. So, and we know that the smoking is only 5 times like more dangerous than like being outside in urban air or so, right? So it has to level off somehow. So when we saw this was actually really interesting, right? So that at some point you cannot trigger more oxidative stress or so. So these were also exactly the same thoughts we had when we saw this. However, this is really just the concentration of ROS due to these air pollutants. Actually, now we think it's not a good metric, right? So because just having these ROS concentrations are dominated by hydrogen peroxide, and we actually don't think that hydrogen peroxide is super dangerous. It's really these OH radicals that we have to look at, and there this saturation behavior actually goes away, right? So yeah, we exactly had the same thoughts, and it's really a complex interplay. And at this point, it's still super difficult to say what this really means.
Thank you.
Any other questions? Let me just a comment, or no, in fact, a question. I assume that it's not easy or evident, but just based on the same image and the whole talk. What do you think that this complex question and research could be translated in an effective, how to say, policies, or I mean, how to extract the conclusion, the optimal conclusions to create safe environments?
Yeah, so this is somehow where I started, right? So at the moment, the policy only looks at how much mass of PM 2.5 is there in your city, right? And it might be that your city is very close to the ocean and you make lots of sea spray, or that your city is very close to the desert and there's lots of desert dust in the air, which might all be things that are not super toxic to the lungs. However, when you have lots of power, like plants, like industrial plants, lots of traffic, brake wear, what comes out of the exhaust pipes and so on, these compounds, this is what our model looks at and also ascribes a high toxicity to. So we somehow have to go from just looking at the mass to looking at the actual composition of these particles. So what I really hope to do with our models is to find, instead of looking at just the mass of PM 2.5 in a given city, maybe look at something like the production of OH radicals. Maybe look at something like the production of these biomarkers to translate. You need the mass of particles in one hand, and it's important, right? You see it goes from bottom left to top right, but there's lots of variability also here. It spans several, this is an order of magnitude spread between these points, and we have to take this into account as well. So this, I hope, so the goal of my research is to find some kind of other marker than just, it has to be simple, something like, and also measurable, like PM2.5, which everyone can go out and measure, right? But it has to be more looking at the composition of these particles.
Thank you. And
yeah, so there's a question first there.
Hi, thank you for your talk. It was really interesting. I have a question about what you think. I know it's not exactly your field of research, but what do you think about the scale of how good the air quality is? Do you think that the scale is well organized considering the effects that the air quality has on our health, or do you think that what we now think is okay is not exactly what is healthy?
Yeah, this is super interesting, and there's lots of opinions here, and the honest answer is we don't know enough yet, right? So one thing, so what I mentioned here is, right, so these are the different guidelines. So the WHO, I think just a few years ago, so they updated their recommendation, and they said all countries around the world, they have to work on reducing the air pollution to under 5 micrograms per cubic meter, which this is the most aggressive guideline. And you actually see that the US has a much lower guideline here with 10 micrograms than the EU with, I think it's 25. Which, by the way, it depends a little bit. The EU is much more densely populated, so we just have higher PM2.5 concentrations here. And then also China is more densely populated than the EU, so they also have higher. So it's also that these governing bodies, they kind of adjust their guidelines a little bit to what the situation is. And then you can already see there's no scientific background to this. We cannot, and now I hope I can go to the very beginning again. So here you see this is what comes from epidemiology. And they don't really know where it starts, right? So maybe it starts, because you cannot, there's no human being that lives at 0 micrograms per cubic meter, so we have no one to compare to, right? We don't know how long we would live if we were exposed to 0. So here we just cannot know. And with everything in life, right, it's somewhat of like a risk assessment, right? Are we willing to accept, let's say, a 10% increase in mortality, right? Are we only willing to have like a 5% increase or so? I think this is really something that decisions we have to make on an individual basis, right? How much would it cost, right? What would be the cost to the economy, or do we have to install like air filters everywhere in our houses or so in order to reduce this impact that we have? But what's clear from my side is that, well, 10 micrograms is better than 20. Right? So reducing the air pollution anywhere you live, it seems to be somewhat linear in this range where we are, right? I would assume that right now outside we maybe have around 20 micrograms per cubic meter because it's a sunny day, right? It is a linear response, so reducing it would definitely help.
Thank you.
Yeah, also related to the toxicity of the different particles, do you know if there are any studies that show like different particles can derive in some different, I don't know, diseases or conditions, or all have the same, it's the same for us, but also the toxicity makes it worse, or?
So you mean in terms of if there are different like disease outcomes with different particle types?
Yes, like in different regions or different cities, like we have maybe a different pollution than in another city with more dust or something like that. So if we have the same pathologies or not?
Yeah, for sure. So this is a very complex answer, I think, that one would have to give. It definitely is the case that there are some places we have lots of these natural aerosols, like sea spray or desert dust. That seems to be less toxic than these like urban traffic exhaust particles. What's really interesting, and maybe this is one thing I can share from the current discussions in my field of study, is that when you look at car exhaust, so there are some particles that come out of the exhaust pipe from the combustion process, and there's some particles that come from the brakes. And now that we transition from like exhaust, from like combustion cars to electric vehicles, right? The combustion exhaust, that goes away, but the brake wear and the tire wear, that stays, right? And we're not quite, it's really not clear which one is more toxic, right? We know we're going to reduce the pollutant impact to some extent, but it's possible that we only reduce it to half, even though we would think electric vehicles are much better, maybe they are only a little better, right? And this is really something, this is active research at the moment that people are looking at. We think it's mostly, so I think a general guideline is that you have these, that combustion aerosols, that combustion particles, seem to be the most toxic ones, right? So everything where you burn stuff, that's usually very toxic. And then you have some weird special things. You might have heard of asbestos, right? So these are very specific particles that have a very specific structure that kind of they are not cleared from your lung because they are so long fibers, they just get stuck there, right? And this is why they are so dangerous. But this is a very specific kind of side topic. In general, what we have in the urban atmosphere, I would say like combustion aerosols seem to be the most dangerous ones.
So thank you, Thomas. It was really, really great, great talk. It's also a great example of another kind of models that is being applied. So now chemical kinetics models that has also its hypothesis, its context of use, and that brings very valuable information. So I don't know. So if I go to the Meteo app of my phone, so actually I have a section which is air quality. So I'm on iPhone, so native app on my iPhone has this. I don't know in Android. You can check. And that's interesting then to see. So we do, so currently, so here in Glorias, Barcelona, we have 11 micrograms per cubic meters of PM 2.5. Mm-hmm. And the main pollutant is ozone with 40 ppb.
Okay, it's quite high.
Yeah, so I don't know where we stand.
Yeah, so it seems like particles not so high today. Maybe it rained or so in the last days, that's possible. Yeah. But ozone seems quite high, right? So this is because urban emissions, lots of photochemistry going on because it's the summer, and then you make lots of ozone.
Yeah. And then it shows, so I guess now with this knowledge of ozone, so we could infer on so how much risk of exposure we could have to this hydroxide radical.
Yeah.
And I think it's super example also then to see that the information that is here is actually probably not sufficient because of this lack of metals and so they deem that the quality of air is correct. That's what they say here. So I don't know what is your assessment.
Yeah, exactly like you say, right? It's a bit of a measurement problem. So measuring PM 2.5 concentration is very simple. You just need one instrument you put up somewhere, and then it just runs and gives you data. What's hard is to measure the composition, right? And now you could, of course, say, well, you can measure it once for a given city, and now you know you just assume it's always the same, but it's not, right? It really depends on meteorology, what season it is, and so on. So the best thing would be to have like devices that measure the chemical composition of these particles, but this is very expensive to do, right? So there's really where I hope that at some point models like, so the lung model that we have, and then other models that model the composition of air in a city, right? So they can come together and then provide these better metrics, right? Because right now it's like someone like you or any interested person look at the app and sees, okay, it's somehow ozone, whatever this is, it's high, and PM 2.5, whatever this is, it's medium right now, but it doesn't tell you anything, right, about what it really means for your health. So I think we need more computational tools like these to translate this information to something that actually lets you know what happens in the body with you.
And another question, how about plastics, microplastics, are also in the environment, right?
Yeah. Yeah, I think we don't know yet at all.
Not at all.
I think from the chemistry side, I think they're pretty dead, so they don't make much chemistry. But there's a whole different aspect to this work that I have not talked about today at all. is what do they do with the triggering with the immune response, right? Because also these particles, they trigger macrophages and so on. And if you have something that's a microplastic that the body cannot get rid of, right? Then we're again in the same, talking about the same stuff with the asbestos, right? Where you just have some object in your lung forever and ever, and it just and then your body produces lots of stuff. So, open question.
Yeah, they definitively accumulate.
Yeah.
They definitively accumulate. They definitively pass the blood organ barrier, and they've recently found that it passes blood-brain barrier, including, which is normally very poorly permeable. So yeah, we're full of plastic. We're becoming more and more synthetic. Yeah. So just as a final word, and before Bea can close the session, so we are very lucky. So three of us were involved in a European project that has just been granted. So it's coordinated by Bea. So Bea announced it when she was introducing Thomas. So if this is a field that interests any of you, so in the next, starting the next year, there will be opportunities for bachelor thesis. There will be an opening also for a PhD thesis. So you still have to do your bachelor thesis, your master. It's a bit far for you, but yeah. So there will be then opportunities to work in that field, biochemical part, also on the computational biology part, and also on the lung mechanics part, because the inflammation, so Thomas talked about inflammation, and inflammation is not independent from the stretching of the lung parenchyma when we're breathing. So actually, so that there is actually then feedback loops between mechanics, sustained inflammation, deposition of particles, and so the oxidative stress in this lining fluid. So yeah, just to let you know, it's kind of a new field that's coming.
So thank you, and enjoy the dinner. Well, I don't know if it's the time to take lines.
Yeah, so it's
Okay.
it's basically closing the session, no?
This one.
Yeah.
Okay. So
Yeah.
thank you.
Thank you again, Thomas.
Thank you, Thomas.